Let's take a look then at the equivalence point. We can actually easily calculate for the volume of the equivalence point because we know that the moles of acid and base are equal. So 0.01 molar 10 ml, 0.01 molar 10 ml, sorry, I'm getting ahead of myself, volume of acid should easily show us that the equivalence point happens when 10 ml of hydrochloric acid is added. So at 10 ml, the millimole of HCl added is 10 ml times 0.01 molar or millimole per ml, which is, surprise, surprise, 0.1 millimole, which is also the millimole of sodium hydroxide initially. If there are equivalent amounts of hydrochloric acid and sodium hydroxide, then that means there are neither hydrochloric acid or sodium hydroxide to determine the pH for the equivalence point. So, the only other acidic or basic species left in the solution is water. If you could recall, water is both acidic and basic because it can form hydroxide and protons. I may have said that the other way around. This is a very weak acid or a very weak base. If you could quantify the extent of the appearance of the products compared to the reactants, and we can do that easily by describing the equilibrium constant. For water, the dissociation constant, or H plus OH minus, the product of the concentrations, is 10 to the negative 14. Since the concentrations of both the proton and the hydroxide are equal, we could easily show this as a square, meaning that the hydrogen ion concentration is 10 to the negative 7. So the pH at equivalence point is negative log the hydronium ion concentration or the hydrogen ion concentration. Negative log of 10 to the negative 7 is just pH 7. Alright, so you should have already had some idea that the pH would be 7 because again there is no acid or basic species left to contribute to the pH. Let's now do the final region beyond equivalence point. Let's consider 15 ml added. With 15 ml of HCl, hydrochloric acid now becomes the excess reagent. So, if we subtract the initial millimoles of sodium hydroxide, this is 15 times 0.01 minus 10 times 0.01, 0.05 millimole HCl or hydrochloric acid, this is in excess. Again, this is the product of the neutralization titration or the neutralization reaction. If we started with 0.15 millimole and we had 0.1 millimole, after they react, there should be 0.05 millimole of hydrochloric acid remaining. Since hydrochloric acid is an acid from its name, it is a strong acid, meaning that all of it is converted to hydronium ions. If we start with 0.05 millimole, we also end up with 0.05 millimole of the hydronium ion. Meaning the pH is the negative log of the hydronium ion concentration. So that's negative log 0.05 all over the total volume, which is now 10 ml plus 15 ml. Notice this is millimole per ml. So it's always the molarity. Calculating for that, 0.05 over 25, the pH is 2.70. Let's tabulate everything. So volume HCl added, and then the pH. We looked at 0 ml added, 5 ml added, 10 ml added, and 15 ml added. 2.7, 7. For 5 ml, it was 11.52, and then it was 12. Using these values, we can now generate a hypothetical, theoretical titration curve. So again, in the x-axis, it's the volume of titrant. Y-axis, it's the pH. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, pH 7, 8, 9, 10, 11, 12, 6, 5, 4, 3, 2, 1. Let's try to plot this. So there are some missing information near and slightly above the equivalence point, and the pH there drastically changes, right? So it's smart for you to calculate for those values, but let's say for now that we only consider these 4 pH values. So let's plot them. At volume of hydrochloric acid 0, the pH is 12. At 5 ml, it's 11.52. Let's say it's over here. At 10 ml, that's pH 7. And then at 15 ml, it's 2.7. Let's say it's somewhere over here. So the titration curve should look like something like this. Phenolphthalein is still a good indicator for this because since the equivalence point or the steep region is there, remember that the phenolphthalein range is from around 8 to 9 or 10. So since it coincides with the steepness of the titration curve, phenolphthalein is a viable indicator. Okay, so this has been a long video, but these are things that you already should have known, so it shouldn't be too much to consume. However, we do need to review some information about weak acids and weak bases, because what would happen if we did a titration involving a weak acid or a weak base? How might we calculate for the pH in those instances? Well, before we continue, it's important that we first have discussed strong acid and strong base titrations.